In the early days of aviation, the only form of aircraft brakes was the tail skid. Though primitive in design, it was an effective means of braking. As the airplane touched down at very low speeds, the skid dug into the dirt, resulting in a very short landing roll. As runways became paved, tail skids gave way to tail wheels with brakes installed in the main wheels. And with only a few thousand pounds of weight to stop, the pilot could feel when the aircraft tire began to go into a skid and react accordingly. Today's modern jet aircraft present a new problem for effective aircraft braking in all weather conditions. These aircraft touch down at high speeds on small diameter tires inflated with very high pressure. This only allows a small contact area with the runway surface. And coupled with the fact that many of these high-speed jets use a multiple of wheels, the pilot is often unable to feel individual condition of the wheels as he applies braking pressure. Now, to overcome this problem, modern aircraft technology has developed a modulated anti-skid braking system to allow maximum braking no matter the weather, without the danger of flat spotting or blowing tires from a locked wheel condition due to an actual skid. To learn more about this new technology in aircraft braking, the Aircraft Wheel and Brake Division of the Goodyear Aerospace Corporation presents this training program on typical aircraft anti-skid braking systems to help you, the professional aviation maintenance technician, better understand these vitally important systems. When an airplane touches down on the runway, it possesses a tremendous amount of energy because of its weight and velocity. And before the airplane can be brought to a stop, this kinetic energy must be transformed into brake heat and other drag forces. To stop the airplane, the pilot applies the necessary braking force, which slows the wheel's peripheral speed below that of the airplane, causing the tires to grip the runway surface, slipping slightly, but producing a great deal of tire drag. Now, as long as the tire is slipping on the runway surface, it provides an effective stopping force. And as this slip increases, the stopping force becomes greater, but only up to a certain point. As soon as slippage becomes excessive, the braking force decreases rapidly, and a true skid condition develops. Now, at this point, it is only seconds before the tires wear through, blow out, and control of the airplane can be lost. To understand how an anti-skid braking system works, let's look at an aircraft without an anti-skid system. Here, when the pilot applies the brakes, the brake pressure rises and the wheel decelerates enough to cause the tire to slip. If this braking pressure is held, this slip will continue to increase, reducing the tire and runway friction rapidly, causing the wheel to lock up. If this continues for more than a few seconds, the tire will wear through and blow out. Without an anti-skid braking system, the pilot can usually detect a skid condition. But by the time he releases the brakes, a certain amount of time will lapse before the wheel spins up and he applies the brakes again. Now, this method uses more runway length and time to stop. From here, let's examine early anti-skid systems which were developed to automatically sense wheel deceleration, wheel lockup, and the rate of wheel speed recovery. In these early systems, the brakes could be automatically applied or released, but the slow response of the early skid control valves caused brake pressure to often go above the skid threshold before it was released or dumped. As a result, these systems were often ineffective and even caused the skid to be more pronounced, thus requiring more time for recovery. The modern type of modulated braking system overcomes these problems by allowing brake pressure to increase until it reaches the skid threshold, then cycles the pressure with small excursions to hold the wheel at the skid threshold for maximum tire drag. The heart of this system is the control box, containing electronic skid control and modulator circuits. Now, these circuits monitor the wheel speed signal and control the brake pressure automatically. The special anti-skid valve used in this new generation of anti-skid braking systems is an extremely fast-acting electro-hydraulic servo valve, which regulates the fluid flow to the brake. This is achieved by a continuous command from the control circuitry. By rapidly releasing and applying a controlled amount of pressure above the nominal skid pressure level, the wheel speed is held in the critical slip area, permitting the plane to be stopped in the shortest distance possible without the danger of flat spotting or blowing the tires. Another feature of modern anti-skid braking system is that when the wheel rotation is below approximately 10 miles per hour, the anti-skid system is inoperative, allowing full braking control by the pilot for taxiing. During this condition, the wheels may lock up, but at this speed, tire damage will not result, and the danger of the pilot losing control is negligible. Well, now that we are familiar with how a modern anti-skid braking system works, let's review the components involved, how they operate, and basic troubleshooting procedures. There are three basic components of an anti-skid system: the hydraulic valve, a control box, and a wheel speed sensor. The anti-skid valve consists of a torque motor which receives signals from the control box. Here, a spool-type valve directs hydraulic fluid pressure from the pilot's brake control valve to the brake, or from the brake to the system return manifold. The anti-skid valve is located in the line between the pilot's brake control valve and the brake. When the anti-skid system is off, or when the wheel speed is below approximately 10 miles per hour, or a normal no-skid operation exists, this valve is passive, which means the brake pressure is directed to the brakes and the valve has no effect on the system. But when a skid does occur, let's say on the left wheel, the left anti-skid valve will dump the pressure from that brake back into the system return manifold until the left wheel starts to spin back up. Then the pressure will be automatically applied again. This action is independent of the brake control valve operated by the pilot, and the brake pedals can be fully depressed all of this time. When the brakes are applied by the pilot and no skid is produced, the anti-skid control box does not activate the torque motor coil in the anti-skid valve, and a flapper, centered between two nozzles in this unit, maintains equal pressure on both ends of the spool valve. Now, this causes the fluid from the brake control valve to go directly to the brakes. But when the torque motor receives a signal from the anti-skid control box that a skid is developing, this flapper moves over, restricting one of the nozzles and opening the other, to unbalance pressure on the lands in the spool, moving the spool over. By doing this, the pressure port is sealed off and the brake port is connected with the return port, dumping brake pressure. The extreme sensitivity and rapid action of this type of valve modulates the pressure to the brake, applying only enough pressure to hold the wheel in the critical slip area. The next component in a modern anti-skid braking system is the wheel speed sensor, of which there are two types, AC and DC. The AC transducer is a variable reluctance frequency generator which uses an exciter ring to generate an AC signal. This frequency varies according to the wheel speed and is fed into the main control box where a converter circuit changes the varying frequency into a direct current signal that is proportionate to the wheel speed. With a DC type of sensor, the signal is developed by means of a small permanent magnet tachometer generator located in the wheel axle. Here, linear voltage is developed proportionate to the wheel speed. For example, 1/10 of a volt generated equals approximately 1 mile per hour rotation speed. This compact DC wheel speed sensor is mounted in the axle of the aircraft landing gear, where a special blade attached to its shaft is driven by the slotted drive tube installed in the wheel hubcap. Many of the anti-skid systems employed in today's corporate aircraft utilize the DC tachometer generator system. To understand how this type of system operates, let's analyze the various components during a typical landing. The control box, features, and functions will be discussed as a part of this analysis. Here, prior to touchdown, 0 voltage is indicated from the wheel speed sensor. This signals the locked wheel detector circuit located in the control box to hold the control valve open to the system return, and this prevents pressure being applied to the brakes. As soon as the airplane touches down and the wheel spins up, the speed sensor immediately produces a voltage, which is sent to the skid detector and locked wheel arming circuits in the control box. Now this releases the control valve, allowing pressure applied by the pilot to go directly to the brakes. As the brake pressure increases to the skid level, the wheel decelerates until the tire reaches its critical slip condition and begins to skid. When the wheel deceleration exceeds a threshold level, the skid detector circuit in the control box sends a signal to the anti-skid control valve to reduce pressure to the brake. Now, at the same time, this signal is passed to the modulator in the control box, which acts as a memory circuit to hold the average brake pressure near the skid level. As soon as the wheel stops decelerating and starts to spin back up, a signal from the control box automatically causes the control valve to reapply pressure to the brake, but only long enough for the wheel to again reach its skid threshold. As long as the brake pedal is depressed, calling for full braking, the control box will provide these signals at a high rate of speed to alternately apply and release the brakes, holding the wheel in the optimum slip area. As soon as the wheel speed is down to about 10 miles per hour, the anti-skid system will automatically deactivate, giving the pilot full braking control for taxiing. Any anti-skid system should be simple to operate, and provision should be made to ensure proper operation under all weather and runway conditions. If the speed of one of the wheels drops below approximately 10 miles per hour, while any other wheel is turning more than approximately 20 miles per hour, as will happen if a wheel hydroplanes on a wet runway, the locked wheel detector circuit will automatically dump the pressure to that brake and hold it dumped until its speed builds back up above 10 miles per hour. A squat switch on the landing gear will hold the locked wheel arming circuit energized before landing, so the locked wheel detector will hold the control valve in a dumped position so the brakes cannot be inadvertently applied before touchdown. But when the wheel spins up on touchdown, the voltage generated by the wheel speed sensor will override the squat switch, and the brakes may be applied even before the full weight of the airplane is on the struts. A warning light may also be incorporated into the circuit to indicate to the pilot any time the anti-skid system is not operational. Now, this allows the pilot to plan his landing and apply the brakes accordingly, minimizing the danger of skidding. The anti-skid test system will vary with the different aircraft. For example, on the Falcon 20, when the airplane is on the ground and 700 pounds per square inch of pressure is applied to the brakes, the test light will illuminate. And when the anti-skid test switch is depressed, a simulated spin-up signal is sent into the system, testing the electrical and electronic integrity of the entire circuit, including the speed sensor. Now, if all the circuits are working properly, the test light will stay on as long as the switch is depressed. But when the switch is released, a simulated lockup signal is injected into the circuit, which will momentarily lower the pressure to the brakes, and the test light will go out and come back on in a few seconds. When the airplane is in the air, the squat switch on the landing gear changes the system test logic. The pilot must apply greater than 700 pounds per square inch braking pressure to actuate the pressure switch in the line. Now, this pressure will not be applied to the brakes until the test switch is actuated. By doing this, the test light will illuminate. Releasing the test switch will cause the brakes to release, and it is in this position the test light will automatically turn off. By depressing the test switch, a wheel speed signal is injected into the control box. This causes the light to turn on, signifying that the system is fully operative. If the test lights do not go on, this indicates there is a malfunction in the anti-skid system, and the pilot is alerted to the absence of anti-skid protection. Other than this, braking action will be normal, and he can turn the anti-skid power system off to avoid isometrical braking. In the event of a system malfunction, troubleshooting may be performed by a professional aviation technician in the field to return an airplane to service in a short amount of time. In order to do this, first check the units that are most accessible. For example, in the Falcon 20 anti-skid system, we should begin troubleshooting with the wheel speed sensors. Here, a tweak test may be employed to check the entire system for operation. With the hubcap removed and pressure applied to the brakes, spin the sensor blade in the direction of wheel rotation with your fingers. You'll only get about half a revolution, but it is the rate at which it is spun and stops that's important. If the system is operating properly, the brakes will momentarily release and reapply. This may be seen by watching the discs. If the brakes do not release when the speed sensor is tweaked, it is possible that the generator is defective. Now, this may be further checked by removing the connector from the back of the wheel speed sensor and checking the resistance of the armature as the blade is rotated. In this test, use an accurate ohmmeter and measure the resistance as the blade is slowly rotated through 180 degrees. The resistance should be between 250 and 375 ohms. Also, check the polarity of the sensor by setting the multimeter to the lowest DC voltage scale and holding the positive lead on pin B and the negative lead on pin A. When the blade is tweaked in a clockwise direction is viewed from its drive end, the meter should read upscale. If the wheel speed sensor checks out all right, replace and safety the connector plug and carefully reinstall the hubcap. Be sure the drive tube is not loose and it fits properly over the blade of the sensor, and the alignment rivet fits in the hole in the wheel. Finally, be sure there are no dents in the cap. The next logical step in troubleshooting is to check the control box. Assuming there is an indication that the left anti-skid system is inoperative, remove the two plugs from the anti-skid control box and reverse them. If the malfunction indication stays on the left, in all probability the trouble is not in the control box. But if the malfunction changes to the right side, the control box is defective and should be replaced. Here's a warning. After connectors have been swapped, be sure that they are placed back on the correct receptacle. The only other component in the anti-skid system left to test is the control valve itself. Since this is an electro-hydraulic device, the problem could be either electrical or hydraulic. To check the electrical integrity of the control valve, an ohm meter reading of 500 ohms should be indicated between pins A and C. If regular braking is normal, but the brakes will not release when the speed sensor is tweaked, and after testing the wheel speed sensor, control box, and the coil of the control valve, the most probable cause of trouble is in the control valve, and it should be replaced. The most probable cause for control valve failure is fluid contamination. For this reason, valve manufacturers have made provisions for reducing this malfunction. Typically, a 15-micron steel mesh filter is installed in the valve, and it may be replaced by the manufacturer or his authorized service facility in the event of valve failure. These valves may leak between the manifold and valve assembly. This joint is sealed with special O-rings which may be replaced in the field after the valve has been removed and taken into a contamination-free work area. Caution! Before attempting any repair to the valve, be sure to check with the manufacturer to ensure that you have the latest service manuals. Modern anti-skid systems are a vital part of the aircraft braking system. For this reason, during any troubleshooting procedure, be sure to check the entire system for malfunctions. Be sure there is no air in the system and that the fluid to the brakes is perfectly clean. Air, for example, will cause spongy braking action and reduce anti-skid performance. And contaminated fluid can cause the brakes to drag. Misadjustment power brake valves can hold pressure in the system so the brakes will not fully release. Keep in mind, this program has used the Falcon 20 anti-skid system as a typical example. While other general aviation anti-skid systems operate in a similar manner, there are differences in each system, such as single and paired wheel control, inboard and outboard wheel control, different types of test logic circuitry, plus other features. So be sure to consult the manufacturer's service manual for specific operating information. An accurate knowledge of the operation of any anti-skid braking system gives us the ability to recognize problems before they become serious, to correct them, and return the airplane to service in the shortest amount of time possible. For this reason, it is hoped that this program has helped you to understand more fully this important system on our modern high-speed aircraft. For further information regarding these and other systems, Write Goodyear Aerospace Corporation, Aircraft Wheel and Brake Division, 1210 Massillon Road, Akron, Ohio, 44315. Or write the Aviation Maintenance Foundation, Box 739, Basin, Wyoming, 82410.